I do kind of think this MH stuff in Monte Carlo, you don't really understand it until you code it up. If you're able to implement something, in some way you get it. You know, you at least know what to do, or at least you're able to perform the activity and then fill in the theoretical gaps. So, okay. Today, let's do Jeffrey's prior. We'll just write down what it is. So the Jeffrey's prior. I'll just give us some notation temporarily. I don't think people normally do this. I'll just put a J there. Actually, let me put my J up top. So I think I'm going to use the subscript eventually for some transformation notation. So J, theta. So J is for Jeffrey's. It's going to be proportional to the information half power. The information can be written down like this. So let's just fill this in. This is Fisher's info. Let me write down what Fisher's info is. This is always true. I'm going to write it down slightly different than the way I wrote it down last time. I'm going to write it down with the sampling distribution. I could have written this down as the likelihood function because I'm operating on theta inside of here. It doesn't matter. They're only off by a constant. Again, when I wrote this down, we're only defining everything after proportionality. So the Jeffreys just shows you the shape of the distribution. And if it's normalizable, you'll need to normalize it. And if it's, here's kind of a rough rule of thumb. If you're in an unbounded space, you're not going to get a proper prior. You're going to get something that's not normalizable. So we're going to get back to those same priors we've been using. So this is the first derivative. This thing is squared. And I said that we're operating on theta inside of here, and that's why sometimes I'll say log likelihood. But if you write down the sampling distribution, that's also correct. It's the same formula that you're writing down. I don't care what normalizing constants you put in here. It's just going to zip something. It's just going to cancel it out anyway. Because as soon as I take a derivative with respect to theta, the log of that normalizing constant is 0. So it never even appears anywhere in there. But the expectation that I'm taking is over x. So just to be clear, we're operating on both x and theta. So I'm averaging the x's away, averaging them away, and getting a function over theta. So that's the information. So in high dimensional space, you do this instead of squaring everything, you product it together with its vector. And you can do this in a big outer product and form a matrix on everything. So you would change all of this in high D to this sort of thing. d theta I log fx given theta d theta j. So the elements are just going to be these things. These are partial derivative signs, if that's not obvious. I've never really been one to care. So you just take the derivative. If that's a vector or something like that, and you do all the ij pairs, and you load that into a big matrix. So oftentimes when I do this, just out of habit, I say Fisher's info matrix. If we're dealing with a one parameter model, that's a 1x1 matrix. So it's still true. Sometimes this is true. We can write down the info using this form. D, the second derivative, theta squared, log, I say likelihood because I'm operating on theta, but it's still the same equation. This log is just around that. You gotta be careful, this is a minus sign out in front. So minus. I want to point out, this is always positive. So I know you can't see this, but this expectation right here is negative. When I throw the negative sign in front of it, it makes it always positive. So I just want you to be aware of that. If you ever do this calculation and you get something negative, it's either because you used this formula and you forgot that, or you made a bigger mistake. And you need to go back and figure out where it is. This thing is always positive. You can see that in the upstairs thing. I like thinking about both of these forms right here. So I like thinking about this one because it tells me it's always positive. Expectation of positive stuff is positive. But I kind of like thinking about second derivatives because they tell me about curvature of the space. So it makes me think about, okay, this has something to do with the curvature, the expected curvature of that space. And we're going to form priors proportional to that. It's kind of interesting. If you're familiar with the Kramer-Rao lower bound, you did something else with the information, you inverted. So you put bounds on things. So that was kind of cool. They're not related to each other.
When is that second method not true?
Somebody help me answer this. When is this true?
The second derivative is
Obviously, you need existence of all of the functions in here. Yeah, it's Fubini's theorem. So Fubini's derivatives and integrals can be interchanged. So if those of you that are trying to draw on previous experience Kramer-Rao lower bound, it's the same condition for when you can do the Kramer-Rao lower bound in the first place. Same thing, you need to be able to interchange the derivative in the integral. And I love that in the proof you see that it's true. So if you try to equate these will be equal when you can interchange the expectation, the derivatives in the integrals. There's derivatives here. There's integrals here. So I'm thinking of sums and derivatives. So think about x in continuous space. You know what I mean. If it's a discrete problem, I mean the sum. This is the type of integral. Try to prove this. Try to prove that by Monday. What did I just say? Possible quiz. So, possible quiz on trying to do this. I want to see who can do it. So, plenty of time. No class on Friday. You're reading Gelfand and Smith, or at least doing a heavy skim. Spend a two hours reading through it. So, something like that. And then try to prove that. How many people have done this before? Half of you. So, could you do it again right now? Okay. Not asking you to do that. We'll come back, make sure that we understand when we can do this. It appears right in the proof they are equal if you can interchange those derivatives. So I can end up pulling this derivative sign outside of the integral, and something goes to 0, and it makes the two things equal to each other. It's a beautiful thing. Let me just remind you, recall, if I've got a distribution, so I'm going to say, let's call this pi theta. This is just some distribution I know that I use. Pi is usually when I'm thinking about base stuff, but I'm just thinking about it arbitrarily. Just as any old distribution, so we can match some notation. So if I have this distribution, and then I end up saying theta is equal to g phi. Keep in mind, oftentimes I take the g over here, and that's g inverse. Just want you to get used to thinking about what you actually have. I can relate these two things, or let this be 1-to-1. If it's not 1-to-1, break it up into 1-to-1 regions and apply these formulas to those regions. So if I wanted a distribution on phi, what I do is I take my distribution on theta and I plug in g of phi. But I can't just do that. It's just a new name for theta. I have to also stretch the space. So I end up taking g theta d phi. If you don't like writing it that way, this means dg phi d phi. Absolute value. Why the absolute value? The rough answer is we know this thing has to be positive, but the real mathematical thing, a little bit of chain rule in there is why that derivative is there, and then the increasing, decreasing function. So that's true. We're pretty equipped with this. I'm going to prove this in a moment. So we'll prove I theta, and if you'd like me to write the theta down here, I could. I'm just going to omit it, because what else is it a function of? It's a function of theta. This is going to be equal to I phi, give myself some room, I phi times the derivative of theta d phi. That's right. Squared. So I'm going to have this squared sort of effect right here. It's just like this. Same thing, but it's off by a squaring. So here's what it says. If I take information, and my friend computes the information on a different scale, if he wants to be equivalent to me, he has to do this Jacobian thing and square it and multiply it into it as well. Stretch the space, but square it. Where's the squaring coming from? The definition of that expectation. So that squared sign right up there at the top of the board. We'll see this in a proof in a second. So we'll prove this, that basically I can just move back and forth between these two things, just like I would have done over here. Let me actually just rewrite this. I think I actually have it wrong. Let's just follow the notation exactly. I think I did it in the wrong way. This is going to be this thing. Let me do it here. I'll follow the exact same notation like we did over here. This is going to be g phi right here. So this is just going to be a new way of writing theta. And now d theta d phi squared. That's true. You can almost see it right here. Proof is like a line or two. If you look at this thing right here and I wanted to transform to another space, I can't just take theta and replace it because I'm taking a derivative right here, so I need to do some chain rule. And that chain rule is getting squared. So there's good reason to think that this is true. So what do we do to this to make this form look just like that? I take the half power of it. Get rid of that. So what that means is that informations are transform invariant all by themselves. They automatically get that Jacobian term in there. That's just what happens. You don't have to compute it up front. You just have to know that. So this relationship is very similar to this relationship. This is how you transform parameters back and forth to each other. And the information has that relationship baked into it. It's magic. It just happens for you. So what that means is that if scientist 1, or I'll say statistician 1 or Bayesian 1 computes pi theta Jeffreys. How do they do it? They use this formula right here. Bayesian 2 computes pi phi Jeffreys. I don't mean he takes this guy's prior and transforms it or anything like that. He could have done that. But I mean that he just has his own ideas. He uses Jeffreys' prior, re-encodes this in terms of phi, and Bayesian 2 does this. Has this parameterized just right and does phi right there. And computes everything on their scale. They just plugged and shoved, used a different formula. Keep in mind that little chain rule is going to do some weird things for you. It happens automatically. But they just compute and they use this rule, that's their prior. Then, if they end up transforming back and forth using this formula, they'll actually have the exact same answer. So if you went through the effort to compute this thing, I'll say this is theta, and this is phi by using the relevant formula, and you transformed them back and forth using that formula, you would get exactly the same thing. Let's just show that that's true. Let's do an example. So here's Bayesian 1. Bayesian 1 likes to think about variances. So they're on V scale. So Bayesian 1. They have this model, V to the 1/2 e to the minus 1/2 x minus mu squared over b. Does anybody recognize what this model is? It's normality. So they've got f of x given mu v. I'm going to say this is known and fixed. So they're going to try to come up with a prior. And they're going to use Jeffreys' form to do it. Don't know what to do, but I read about this thing in class. People oftentimes default on it. I don't like thinking. I don't like thinking about what the meaning of the parameter is. I'm just going to let the likelihood just do it for me. So don't like Scotland's conceptual reasoning for why he picks priors. I just want to do a calculation. So let's do it. So they're going to use Jeffreys maybe. So let's just do Jeffreys, see what happens. This is going to be the expectation, and I'm going to use this form. I probably need to verify this to see if I can do this, but it turns out you can. And so I'm going to use my more favorite form of doing this, and you'll see why in a moment. So I'm going to take two derivatives, and take the log of this thing right here. V 1/2 e to the minus 1/2 x minus mu squared over v. work through it. What do you think the answer is, just by the way? It's 1 over V. It will be proportional to 1 over V. Great. That's what we want it to be. Then we would feel really great about things. This would come back around and just show us the scale and variance thing through a different lens. So this is going to look like this. Minus expectation. 2 derivatives. So I'll take my first one first. Take that logarithm. Actually, I'll just take the log in one extra step. So this is going to be 1/2 log V minus 1/2 x minus mu squared over V. Take some derivatives. So I'll go 1/2 1 over V is that derivative minus, this is a V inverse upstairs. So this is going to be plus, bring down that -1, minus is a plus, 1/2 x minus mu squared V squared downstairs. I said I can't do this unless I multiply over up on the top, but it turns out I can. Let's do it one more time. One more derivative. Minus expectation. Don't forget this minus sign. Get rid of that. We'll just bring the derivative in. So this is going to be minus 1/2 1 over V squared. And I've got a minus right here. This is going to be the 2 from the exponent coming down. I've already changed the sign right there. X minus mu squared over V cubed. Keep in mind what the expectation is over. It's over X. So I can't just factorize that thing out, but I can certainly just get rid of this thing and slide the expectation right over the top. So let's just drag that expectation around. This is the only place it appears. So what's this thing right here? We could do the integral. Sounds like a fun exercise. Or we could just know what that means. What's the expectation of the squared distance from the mean called? That's B. That's B. Perfect. So that's just that part right here. So this looks like this. Minus 1/2 1 over V squared minus V over V squared. Right here. Then I need to bring that minus sign in here, and I notice that this thing is positive. Be careful on all of this. So this was a cubed down here. So now this is just squared. And this thing is proportional to 1 over V squared. So I made one mistake. I should have called this squared when I did it, because I need to take the half power at the end of the day. So the Jeffreys prior is the half power of the info, and all we've done is the info. So half power all the way through. It's proportional to it. So check for that minus sign. If you do have a minus sign up here and you can't get rid of it, you've made a mistake. So this is our Jeffreys prior. Let's do it on the precision scale. I love this kind of stuff because it's just a calculus problem. So let's do pi Jeffreys on phi scale. I'll square it over here, and then we'll come over and we'll we'll figure this thing out. Actually, I think I'll just work through the information first. So information on phi, and we'll take the half power of this in a moment. This is going to look like expectation minus expectation, two derivatives on phi log. This is going to be phi to the half power e to the minus phi over 2x minus mu. If you do the square one, it's more math, and I'll let you go through it. It really messes things up. You have to solve an integral, probably. That's why I like this second derivative. I'll go to it every single time because it might knock out some parameters for me and make everything simpler. Expectation, two derivatives. Just write out the log. Half power log phi minus phi over 2 x minus mu squared. Minus expectation, derivative there, 1/2, 1 over phi, minus x minus mu squared over 2. So first derivative knocks that one out. Still have another derivative I need to take. Minus expectation, again, don't forget the minus sign. You know why I'm telling you that. Because I need to tell myself that every single time. Otherwise, I would drop it and be like, what's going on here? I probably took a midterm just like that once upon a time. It stuck with me. So one more derivative, half power. This is going to be minus half power, 1 over phi squared. How convenient. Minus 0, even more convenient. That's why I like that second derivative form, is that can happen often, depending on how you parameterize it. So usually I'll pick a parameterization too that works out really conveniently. So this thing, I don't even have to worry about the expectation because there's no x's in here anymore. They just got zeroed out. So what is this? This is going to be proportional to 1 over phi squared. So the Jeffreys prior for phi is going to be proportional to 1 over phi squared half power, which is 1 over phi. And if we did do the transformation between v and phi, we've already done it in class, they have the same information in them. This is guaranteed to happen. So what that means is that regardless of the parameterization you're working with, if everybody agrees that Jeffreys priors have some magical property and they like Jeffreys priors, then they're all saying the same thing. They may have written the formula down differently, and it might look a little bit differently algebraically, but they can transform back and forth and the solutions are exactly the same. So they'll be doing the same Bayesian analysis. I really like that. I think that makes a lot of sense. I could come up with lots of priors that have transform invariant properties, but I couldn't do it in ways that lines up with everything that we've already learned. So those are scale invariant priors that we got, and they're transform equivalent to each other. So I'd say they're the same priors in disguise. So real quickly, if we did this with mu, what do you think we would get in a normal example? What's that?
Uniform.
Constant. So this would be this. Some constant is what you would end up getting. So it's uniform, it's flat. So yeah, you'd get the thing that we used before. So I probably could have just started with this. But I think it's interesting to think about all those other properties, and it's not just one property that we're getting out of those priors, we're getting multiple properties simultaneously. They kind of make sense from other viewpoints, but also now we have an auto tool that we can just go to and calculate something. And if everybody is using that tool, we're all saying the same things. So I'm not saying that there aren't good reasons to use other priors out there. If you knew something about the problem, if you wanted to bound the problem any particular way, you might want to encode that information. But as a default, I would say this is the most common thing that people do. Let's come back next time. prove that this is transform invariant. Again, all we're gonna do is do the chain rule to this thing, and we're gonna have another derivative that pops out here, so that's gonna change that to the other parameter. We're gonna have a derivative, and we're gonna be able to factorize out that derivative, and that's gonna be that squared absolute value thing that I was writing down. And so the proof is really just an extension of that. I'll come back next time, remind you of that. I'll leave you with one more thing. The Jeffreys prior for a binomial distribution, what do you think it is? Beta half half. So that's where that comes from. So it's automatic, and there's other good properties that we get out of that. So it didn't say anything about it being optimal frequentist coverage, the intervals that we would build, but we did get that property. That requires more math. So that was proved in the 1970s, that it also led to this optimal frequentist thing. That's not true for every distribution, but we did get it for binomial. And it was a lot better of an answer than using the normal approximation. So I think there is something to this Bayes stuff. What is it? Likelihood has joint information about parameters in there, but also it has the information and how it relates to the data. And then the prior comes in as kind of this penalizing form. And we know from lots of experiences, it's probably good to penalize around boundaries of spaces, location parameters you don't need to.
So I was trying to think about actually what you just said, where we're calculating the information in the likelihood here. At least that's my understanding of it. And we're saying that the prior is essentially related to the information in the likelihood.
Yeah, half power.
Right, but based on the data. So what does that actually mean, though?
It means do it.
Okay.
Let's come back next time, fill in some of that. Exactly how do I make sense of it and relate it to Kramer route? I don't. So I just don't. But there are admissibility proofs on why you use this versus other transform invariant forms. This kicks all their butts. And that's kind of nice. I think it might be a coincidence that it's the